Hello, we're Team Urania, and this is our elevator pitch. And we developed a fire spotting drone. So the reason for our project is that we wanted to help solve wildfires, particularly in Northern California. It is estimated that in 2018 alone, there was $150 billion worth of public and private property damage. 11 million Californians live in high-risk areas, almost 1 in 3. And the biggest part of our project that we hope to solve is the early part of early fire detection. Mostly because fire growth is exponential. And the classic example is 1 minute of fire would require 1 cup of water to put it out, whereas 2 minutes would require 100 liters, so on 10 minutes, 1,000 liters. And fire suppression in general costs $2 million per square mile. So a lot of money can be saved and lives if earlier fire detection can occur. So we, using our intuition as engineers, decided to mount an IR camera to a fixed wing, also VTOL capable drone. And some of the metrics that we were able to achieve were 42 square miles of coverage per drone per flight, 112 minutes of flight time at around a starting price of $7,500. With our solution, we estimate that in a specific area where the camera on the drone is able to see, there's a 100% chance that the fire will be seen, which comes around to a cost of $8,600 per unit. So to cover the entire area of the specific area in Northern California, we estimate around $45,000, whereas watchtowers, which is the current best solution, would cost around $250,000 because of staffing, because of other training, because of other metrics, and so on. So our final product, what we were able to produce is a full CAD assembly of the entire product, a gimbal design simulation for a final design, fire detecting software with the camera, as well as flight path mapping. Here specifically is the gimbal using a 2-degree freedom. And here's a video to display some of the motor control and some of the camera orientation of following it. So we decided to remove the 3rd degree of freedom based on our prototype because we think that that 3rd axis, which controls the rotation of the camera, isn't actually effective in determining where fires occur and can be eliminated for simplicity reasons.
Looking at our electronic systems, we have a lot of UI right here. This is one of the benefits of our launch ground control software. So there's the inbuilt UI with our purchased drone, off-the-shelf drone, as well as our UI we developed for fire detection that someone staffing one of these drones would be able to use to point out a fire and alert respective suppression efforts. So for our communication architecture, the final production architecture is something we would contract and outsource because we are not PCB experts. But for the purposes of our prototype, our 2 main microcontrollers were an Arduino and Raspberry Pi. Our Arduino was responsible for keeping the camera stable and taking input from our inertial mass unit, controlling gimbal servos accordingly, and sending the IMU data to the Pi. Our Pi read camera input, ran computer vision fire detection algorithm, was also responsible for logging and reporting all data. So this includes time, IMU, GPS images that would be logged and used for debugging in our prototype and ultimately detection in our final product. So for our fire detection implementation, one of the main things our software does with the camera off the shelf we purchased is set it to T-linear mode. So as it comes, the camera does not show absolute temperature, but rather relative temperatures. So our software corrects for this. In the video, you can see we have a toaster on the left where the temperature is appearing at an appropriate level on our camera. So the software also creates a mask of hot regions in the image, detects a bounding box, and finds the centroid of the region. So that will be used to detect exactly where the fire is in space and ultimately report the presence and location of the fire. Some conclusions and continuations. Our most possible or likely point of failure is wire kinking / tearing for any mechanical system. So how this could be mitigated is as a final production system is in use, determining which wire orientations are the most extreme for our gimbal position and whether this falls within the maximum radius of curvature of the wires we're using. Other possible problems coming up are false positives within our algorithm, particularly other sources of heat that are not fire that can be scanned, such as a hot car engine, sun reflected off the water, or any other manufacturer reflective surface. Potential solution: a visual camera on board for confirmation. So if we get feedback that there's a fire here, visual camera pictures, it's a lake, that's just the sun reflecting off the lake. Our pathway could also avoid large bodies, such as lakes. Our use case is also remote, so we're less likely to encounter manufactured objects that would produce false positives, such as a car or like a large reflective surface.
Cool. Thank you. We are Team Urania.